Hello, everybody, and welcome to Notes Part 3. All right, today we've got several things to talk about. First is we're going to talk about types of covalent bonds. We know that covalent bonds means that the electrons are being shared between two atoms. All right, but not all covalent bonds are exactly the same. We have what is known as a pure covalent bond, all right? And then this is where you have an equal sharing of electrons, all right? An example of this would be with diatomic molecules, all right? So something like Cl2 or H2, okay? And when we talk about the bond, right? So we have a bond between two chlorines, and then they have their unshared pairs around them, but we're just interested in the bond. We're going to write these as dots just to get a little bit better idea of what's going on. Because chlorine has the exact same electronegativity, remember electronegativity is how much an atom wants a pair of electrons, you can imagine that these electrons are shared equally between those two atoms. All right, shared equally is a pure covalent bond. So anytime you have atoms that have the exact same electronegativity or incredibly close electronegativities like hydrogen and carbon, you're going to get a pure covalent bond there. All right, most covalent bonds fall under, or many fall under what are known as polar covalent bonds. This is an unequal sharing of electrons due to differences in electronegativity. So let's talk about, we've got carbon, and let's say carbon has a bond to fluorine. Okay, great. Well, we just write it with a stick. But if we're imagining what's going on with the electronegativities, we have carbon, we have fluorine. Well, fluorine is more electronegative. Remember your halogens, your group 17s have the highest electronegativity. So the electrons actually live a little bit closer to that fluorine than they do to that carbon. And because of this, we get what are known as partial charges. All right, and a partial charge is signified by the use of this symbol. It's like a figure eight that you don't finish. It's called a delta. All right, and the one where the electrons, the atom where the electrons live closer gets a partial negative charge because those electrons are a little bit closer. And the carbon here would get a partial positive charge. All right, those again are partial. They are not full charges like ions. That is the partial charge. All right, so let's get this down in words. Because electrons live closer to the atom, this is going to be a little long, the atom with a higher electronegativity. We abbreviate electronegativity EN. Okay. In this case, the fluorine, all right, gets a partial negative charge, and the carbon, spell carbon right, the carbon gets a partial positive charge. Okay, remember when determining electronegativity, you can look at an electronegativity chart or any of the examples we would give you, you'll be able to use that trend, all right? Okay, so we know we have polar bonds, but what does that really help us? Well, it does help us in determining whether or not you have a polar molecule. All right, there is a difference between a polar covalent bond, which we just talked about, which happens all the time, and polar molecules. We're really interested in being able to determine if something is a polar molecule. A polar molecule must have the following. It must have polar bonds. So something like chlorine gas, any of your diatomic molecules, they don't have any polar bonds. They can't be polar molecules. So that's first. The second is it must have a shape that allows for a positive end and a negative end. All right, so how are we going to be able to tell about this shape? Well, we're going to do our Lewis dot structures. We're going to determine the shape just like we have before. And then from that shape and the atoms involved, we can determine whether we have a polar or a non-polar molecule. All right. So we're going to look, what I'm going to do to help us out, because oftentimes this can visually be a little bit difficult, is I'm going to go through the different shapes that we know and talk about instances where they're going to be polar or non-polar. All right. So let's first, and I left you some space to write, let's first talk about the tetrahedral. Okay, a tetrahedral, you can have two situations. You can have a situation where it's nonpolar and polar. So let's talk about the nonpolar. All right, nonpolar would be something like methane, which we've done the Lewis dot structures and stuff before. Remember, this is my model of methane. Okay, all right, well, the shape tetrahedral is very symmetrical, and there's no way just for me based on the shape to tell if there's a top and a bottom. So if I have a tetrahedral and all four atoms are exactly the same, like they are here in methane, then that is going to be a non-polar situation. So something like methane would be considered non-polar. Now, if instead, all right, I have a tetrahedral where, let's say, I have 3 hydrogens and then a chlorine. All right, and I'm going to just omit chlorine's extra electrons for our purposes now. All right, and a chlorine. Well, now I have lost a hydrogen here, and now you can imagine I have a much more electronegative atom here. All right, so what's going to happen is that chlorine is actually going to pull the electrons towards itself, causing this, my fist here, to be the partial negative end and the rest of the molecule to be the partial positive end. So this would be an example of a polar tetrahedral. So again, for our tetrahedrals, all right, our non-polar is if all 4 surrounding atoms are the same. Our polar is if we have a different atom in there, okay? All right, so now we're going to talk about a shape that's always polar, and things that are always a certain way are awfully nice. So now if you end up getting trigonal pyramidal as your shape, it is a pyramid, all right? So it has a top and a bottom. A pyramid, just by the shape itself, they will always be polar, all right? Because again, if we're talking about, you know, what a pyramid looks like here, all right, you have a top side, you have a bottom side. All trigonal pyramidals are going to be polar. Same goes for your bent molecules. All right, anytime you have bent, they will be polar, okay? So for water is our great example, and that's why we're always supposed to draw water like this to show the bent side. With water, oxygen is more electronegative. That gets my partial negative side. Hydrogen gets my partial positive side. My unshared pairs there, just because water is so important. I'll finish it out. All right, our last 2 shapes are similar to the tetrahedral in that we have to figure out what's going on. So for our trigonal or trigonal planar, okay, it also depends. So you have our nonpolar, which remember for BF3, okay, and remember boron is that exception that only needs 6 electrons, so that's why it looks incomplete. All right, this would be nonpolar. Boron's being pulled on evenly in all directions by the same type of atom. If, however, you change one of those out, all right, and now that's a hydrogen there, well, now all of a sudden it's not being pulled evenly. And what happens is this fluorine kind of side becomes your partial negative side. Now, don't worry, you're not going to have to tell me which side is partially positive and which side's partially negative unless it's water. You do need to know that one. But you do need to tell me whether it's polar or nonpolar. Our last shape, all right, is linear. And again, falls into that same situation, okay, where you have nonpolar, okay, linear. So you've got something like carbon dioxide being pulled evenly, all right, on both sides, whereas a polar situation is if you switch one of those out and let's say you put a sulfur there. All right, so remember things like linear or trigonoplanar or tetrahedral, if it's the same atoms all around, then you are nonpolar. If they all of a sudden become different, then you're polar. All right, you're going to practice this on your Lewis dot structure sheet, but we do have still a couple more topics I want to talk about today. All right, and those are what are known as intermolecular forces. But before that, let's just get some terminology. Intra meaning within. We have intramolecular forces. Those are the forces that hold a single molecule together. They're bonds. They're ionic and covalent bonds. Okay, we just don't typically use the term intramolecular, but that's what that means. Now, what we're going to talk about now is what's known as inter. All right, intermolecular forces. When you see the prefix inter, that means between, like an interstate is between states. All right, so intermolecular forces is the attraction between molecules, the attraction from one molecule to another molecule. Intermolecular forces are also known as IMFs. All right, and we have 3 different types. 2 are really important to us, 1 not so much. This one here is very important, and it is known as a dipole-dipole force. This is the force between 2 polar molecules. All right, this is the strongest, all right, of our 3. This is our strongest intermolecular force. Okay. Polar molecules, remember, have a partial positive end and a partial negative end. So I'm going to go ahead and write water. I'm going to write it on its side here just to help us out a little bit. Okay, and remember, oxygen gets the partial negative, hydrogens are partially positive. Well, when another water molecule comes along, okay, with our partial positives and partial negatives here, what happens is you get an attraction between the partial negative of one molecule and the partial positive of the other. That is your intermolecular force. A dipole is just another word for a polar molecule, so that's why we call it a dipole-dipole force, polar and polar. Specifically, what's going on with water is what's known as a hydrogen bond. I think it's the worst name in chemistry, but it's been around a long time, so we stick with it. It's not actually a bond. All right, it is a type of dipole-dipole force. It is the strongest of the dipole-dipole forces. So dipole-dipole is the strongest intermolecular force. Hydrogen bonding is the strongest of the dipole-dipole forces, okay? It only occurs when within a molecule, something like water, hydrogen is bonded to oxygen, or in another type of molecule, nitrogen or fluorine. Those are the only times hydrogen bonding occurs. You should remember this from biology, all right, because hydrogen bonding is very important in many biological systems, all right. It gives water all sorts of properties like surface tension, capillary action. You don't have to worry about jotting these down now. We're going to talk about all of those in a little bit more detail in our last set of notes. All right, moving on, our next type of intermolecular force is what's known as a dipole induced dipole. This one is our least important, to be really honest, because it's in a mixture. Okay, this is occurring in a mixture. It's not a pure substance. We tend to focus on pure substances. This is what would happen between if you have a polar molecule like water and a non-polar molecule like chlorine. All right, and what we say is that we have our water here, and again, I'm just writing it kind of on its side to give a little bit better visual. And it comes near something like chlorine, okay, which remember, chlorine doesn't even have polar bonds, so it's certainly not polar, okay. Alrighty, great. And what ends up happening is because this partial side is here, it gets near the chlorine and these electrons start to shift over, all right, a little bit. And what that does is it induces or it forces this chlorine to have a slight little dipole, a slight charge, okay? So it's a dipole induced. This is your dipole here. Your chlorine then, because it's in the presence of water, would be your induced, okay, dipole. Again, we don't deal with this one a lot, to be very honest, because again, we don't talk about mixtures a whole lot in this unit. Our last one is what is known as a London dispersion force. And this occurs really in all molecules, but it is the only force that occurs in between 2 non-polar molecules. All right, so the only force between non-polar molecules. Okay. And these occur because at any given just random chance, electrons can be concentrated on more than one side, on one side of a molecule. And that just happens at a split second, very temporary. Because of this movement of electrons, you can get what is known as a temporary dipole. Therefore, that can then trigger another little temporary dipole. Very, very weak forces going on. Now, why are these different types of forces important? All right, well, they give us an idea as to the different properties of these atoms. When you have your dipole-dipole, and I just went back a little bit in your notes, when you have dipole-dipole force occurring, all right, you tend to get things that are either solids or liquids at room temperature under normal conditions, all right? Again, as we mentioned, the hydrogen bonds cause water to have a lot of properties that we'll get into later. When you have polar molecules, okay, they tend to be gases non-polar molecules tend to be gases at room temperature. So because they have these really weak forces working on them. So let's talk a little bit about properties, and I know you have to add this a little bit to your notes, okay? Polar molecules, because of the forces holding them onto them, tend to be, all right, now this is not in all cases, but in general, tend to be either liquids or solids. All right, nonpolar tend to be either gases or liquids that evaporate easily, okay, that turn into gases very easily. I'll say evaporates quickly for our purposes. All right. Now you can certainly get some exceptions. Things like oils are nonpolar and they don't evaporate easily, but they are so heavy. They are very large. They have large masses. So they tend to stay liquid. But in general, our polars tend to be liquids or solids because this is a strong forces holding them together. Okay. And our nonpolar tend to have those weaker forces. Okay. All right. So we'll get some practice with this and have a great day.